the kind of discussion of our parameters. Okay, so it looks like it is recording. So we're going to be discussing today kind of the remaining psychometric parameters that we need to talk about. And then we'll probably just get into starting the example problem that we have, and we'll finish that up next week in class. So just a reminder that today is the last day of class for this week. So tomorrow is our 1 day off spring break. So we will not be having class. So if you do want to have office hours or have any questions on the lab reports or the homework, feel free to ask for that period. Additionally, I want to point out that the psychometric quiz for the reading quiz should now be open. So I'll have that due, I think, on Monday. So you do have some time over the weekend. Just take a look at that. It is open book, open note. So it covers kind of the key parameters that we've been discussing in lecture this week. Otherwise, I'm going to try and get the exams that we just took and your first lab reports graded over the kind of long weekend. And I'll try and get that back to you before the end of the weekend. That way you have some feedback for from your first lab report for your second lab report. And then I'll try and get the exams scores posted. And then I will be handing back the exams the next time we meet in person in lab, which is not going to be next week, because next week we don't have a physical lab. So that's kind of be a break week. So it will be maybe 2 weeks before you get the physical exams back, but I'll try and get the scores posted on Canvas as soon as I can. Okay, so I think that was all of the key comments there. Additionally, for those of you who just came in, we are not having the pop quiz that I was joking about beforehand. So if you're in channel beforehand, we were joking that today is April 1st, and there was going to be a second midterm today. There is no second midterm. We are just going to be covering the key continue our discussion of psychometrics. So with that in mind, I did back up a few slides from where we ended yesterday, or not yesterday, on Monday, in terms of our discussion of psychometrics. And so we were talking about some of the key parameters that we need to know and what made psychometrics different from our previous gas mixtures. And so the difference came from the fact that for psychometrics, we have a vapor that could go through a phase change. And so we were looking at water vapor that was outside the vapor dome, and we had to compare that to the saturation state. And so that's kind of the big thing that's changing, and then we had to kind of adjust some of our nomenclature for that reason. We then introduced 2 new parameters for this. We first had the humidity ratio, which was the specific humidity. Again, this was a ratio of the mass of the vapor over the mass of the dry air, and that ended up coming out to this relation that we could use for air and water vapor. And then we also developed the relative humidity, and relative humidity was a comparison of the mass of the vapor over the mass of the vapor at the saturated state. We found that was just a ratio of the partial pressure of the vapor over the saturation pressure at the same temperature. And so those were our key definitions that we used. And we were able to then put these together to kind of come together and see how we could, if we know our relative humidity, we can now use that to find our humidity ratio. If we know our humidity ratio, we can then use that to get our relative humidity. And so that is where I think we left off, and we are now going to start talking about our key properties. Now, for key properties, we are going to mainly focus on the energy properties for right now. That is going to be enthalpy and internal energy. And so we're going to do our discussions first in terms of enthalpy, because it's a little bit easier to kind of talk about. And we're going to see that most of the applications that we're going to have for psychometrics are going to relate to open systems, because it's going to be like HVAC applications. So open systems, that means we're going to be dealing with enthalpy. And so the first thing that we want to talk about is the extensive form of enthalpy. So extensive, remember, capital letter, that is going to be additive. And so that was one of the key things that we noted in the gas mixture section. So if we want to talk about the enthalpy of this mixture now, we're going to have the enthalpy of the dry air, and then we're also going to have the enthalpy of the water vapor. And so we have both of those, and those are going to be the extensive form. Now, in terms of getting this into intensive forms, well, intensive was the per mass basis. And so for air, we could say deal with the mass of the air times now the enthalpy in the specific form of the dry air. So M times small h times of air. And so again, this is just the intensive form of this part. And so we'll make a note that we should also include this is the mass of the dry air as well. And so we can then repeat this process. So the extensive form of enthalpy for the water vapor, that's just the mass of the water vapor times the specific enthalpy of the water vapor. So again, we have these two intensive forms of specific enthalpy now. But now we have to figure out how are we going to model each of these. So for air, we know that we have the enthalpy of the dry air. If we think back, we said air is an ideal gas. Ideal gas, we can say, well, that's probably going to be related to a specific heat for most HVAC applications. And we said, okay, if it's going to be related to a specific heat, we said, well, H can be approximated now by a C sub P of air times the temperature. And so this temperature, of course, is of the mixture. And so again, this is just air being an ideal gas. We can just take advantage of the ideal gas law. Where it gets now a little bit tricky is when we want to deal with the enthalpy of the water vapor. So the enthalpy of the vapor. Well, the answer to this is a little bit tricky. And so we have to kind of visualize this process. And so how do we visualize it? Well, if we go ahead and plot a TS diagram, and then we plot some lines of constant enthalpy on it, and we look at the vapor side. Well, we said in terms of vapor side, most HVAC applications, well, it's going to be kind of generally a low temperature. So if we think of it about room temperature, 25 degrees Celsius, well, if we go ahead and plot this line, we said, well, if we get out to this enthalpy in the superheated region, so that's again because we have a low partial pressure, our point is going to be somewhere out here. We note that the lines of constant enthalpy are pretty much horizontal. And so if it's pretty much horizontal, we said the enthalpy out here is basically the same as the enthalpy here at the saturation point. Saturation point is H sub G. So, and this would be the saturated vapor state. And so we said, well, if these lines are mostly horizontal, that means we can go ahead and do our table lookup for H sub V at the saturation point. So H sub G at the given temperature. So all we have to know is the temperature. We go to the saturation tables, we go to the vapor side, which is of course the G side of the table, and we can look it up. So basically we are assuming this is a saturated vapor. And so that is the approach that we're going to be using. Now I'm going to go ahead and quickly skip ahead here because I want to show this. So this is in the back of your textbook. You have a TS diagram for our water vapor. So this is figure 9A in your textbook. And so we have temperature here on the y-axis, we have entropy on the x-axis, and we have a whole bunch of constant lines. But if we look very carefully, we do have some lines of constant enthalpy. And so we said, well, let's look at some values. And so this is 100 degrees Celsius. We want to zoom in on kind of this region. So if we go ahead and zoom in on this region, we can get a little bit better picture. And so if we say 50 degrees Celsius is right about there, and let's say about 25 degrees Celsius, so room temperature is right about here. Well, let's look. Yeah, it looks like right here, this would be a line of constant enthalpy. That looks to be pretty horizontal. Even if we go up closer to 50 degrees, still mostly horizontal here. Even going higher up to like 75, we still see it's horizontal. And so we can say, okay, that little bit of an assumption, it's not going to be perfect, but it's going to get us close enough that we can kind of say, okay, we don't want to spend all of this time needing two pieces of information to determine that. So we need our partial pressure and our temperature to establish the enthalpy out here in the superheated region. We said all we need now is, of course, the temperature by assuming that we can look it up at the saturation condition. And so it's just simplifying the approach a little bit, saving us some time, saving us some calculation power in whatever process that we're going to do for the lookups. And so, and it's just making our life a little bit easier. So that is the approach. I just wanted to kind of prove that, because this figure is a little bit, I want to call it more of like I hate to call it like a comic version of the TS diagram. So I wanted to show it with the data actually plotted that yes, these assumptions do work. Now, what we often do in terms of enthalpy, and we're going to see that this is one of the most common approaches that we do when we talk about kind of open system and closed system analysis, is we like to talk about the enthalpy on a per mass basis of dry air. So we'll call this the dry air basis. And so this means that we're going to be doing the entire analysis in terms of thinking about air as a dry substance, but we need to include some of the effects of the vapor. Now, what does this mean when we say the dry air basis? Well, if we looked up here, we have the extensive form of enthalpy. And so we said to get the intensive form of enthalpy, so we have small h, this is equal to the extensive now divided by a mass. And so in this case, what we did is we said, okay, we had the mass of dry air, we had the vapor, and we lined those up with each. Now what we're going to do is we're going to modify this approach. What we're going to do is we're going to do, again, on the dry air basis, we'll have the extensive enthalpy, which is the total enthalpy H. And again, this is of this mixture. And we're going to divide it by a mass, but we're just going to divide it by one component. We're going to divide it by the mass of the dry air. Now, why this is important, we will see it come up in our mathematics for our energy balances quite often, that we can apply this, and it will make our life a little bit easier. And so we're going to basically refer to this now as kind of the dry air specific enthalpy. And so it's not of just the dry air, but it's on the dry air basis. And so that would just be the total H divided by mass of dry air. Now what we can do is we can say, well, if we do this setup, I'm going to go ahead and rearrange this. Well, we're going to make this substitution right here. So we have the mass of the dry air times the enthalpy of the dry air. And now we're going to divide by the mass of the dry air. We're going to add in the second component. We have the mass of the vapor, the enthalpy of the vapor, and then we're now going to divide by the mass of the dry air. And so what we're going to do is we'll say, okay, well, this is our specific enthalpy on the dry air basis. So again, dry air basis. Now we have mass of air divided by mass of air. That's just 1. So we have the enthalpy of the dry air. Plus now we have the mass of the vapor divided by the mass of the dry air. And what we'll note is the humidity ratio was the mass of the vapor divided by the mass of the dry air. And so we can make this substitution. And so we'll end up with the humidity ratio times the enthalpy of the vapor. And so for the enthalpy of the vapor, we'll go ahead and make that substitution H sub G. Well, we'll do that here in the next one, actually. So H sub V. Okay. So that is the setup. And we can go ahead and take this actually one step further. Again, this is still on the dry air basis. H sub A, we said that would be C sub PA times the temperature. Plus now we have the humidity ratio. And we said H sub V, this is equal to H sub G at the given temperature. And so now we have these two forms of the equation. This is how we're going to model our enthalpy on the dry air basis. So again, dry air basis, this is the result. And so again, we just divide it through by the mass of the air. Now, can we do the same thing for internal energy if we're dealing with a closed system? Yes. And so we can take the extensive form of internal energy, split that into its two components. So we have the dry air and the vapor. And we could then take the setup that we'd have here, divide through by the mass of the dry air. And so in this case, we would see a similar result. We'd have essentially U of the dry air plus the humidity ratio U of the vapor, which we could then say, well, specific internal energy. This is C sub V of the air times the temperature plus the humidity ratio, and then we have our extra component, which would be U of G. Okay, so that's the approach that we're going to be taking in terms of dealing with the psychometric properties. All right, are there any questions about that?
I had a quick question, sir. So for HG, is that G a subscript?
Yes, so that is the subscript of the saturation condition. So whenever we looked up tables, remember we had over here, we had like H sub F, and then this over here in the table was H sub G. What we're saying is we're looking up the enthalpy in the table. So this would be like our constant temperature, and we're just looking it up on the saturation condition. And so whenever we see H sub G, you're going to go to your steam table. You're going to look up the temperature table for the vapor dome, and then you're going to look up the G condition, which would be the saturated vapor, so the right-hand value. Does that answer your question?
That and then some, sir. Thank you.
All right, good. Glad to make sure that's clear, because yeah, that's one of the more important things to remember when we deal with the psychometric properties. Okay, so we already talked about the temperature, how we prove that the enthalpy is basically constant enough here that we can get away with that. And so what we want to do now is move forward into our discussion of some of the key temperatures that we have for psychometrics. Now, psychometrics is a little bit unique. So in terms of temperatures, there's going to be 3 temperatures we need to talk about. Now, I want to point out this is going to be a little bit different. So up until now, there's been 1 temperature, and that was whatever the thermodynamic temperature of our system was. That's the only temperature we knew. Now, when we did get to gas mixtures, we did add one kind of little caveat to that, and that was whenever we dealt with Dalton's law, Amagat's law, we said we were dealing with the same temperature for the mixture, so we could call it the mixture temperature. And we said that each individual component gas generally had to have that same temperature in terms of kind of the molecules. And so we just said each gas as a individual component had the same temperature as the total mixture. Now we're going to be continuing that assumption. So that does not change. What changes is how we define certain temperatures. So these are more definitions, and they'll kind of tell us something important about what's going on in terms of the vapor and whether or not we have some sort of phase change that we really need to be considering. Now, I will point out some of these temperature nomenclature does get a little bit confusing. And so that's why I did want to spend a little bit of time talking about what are these main temperatures and why do we care about them. And so we are going to spend a little bit of time on definitions, and then we're going to look at a TS diagram to kind of visualize what's the difference in the temperatures. And so the first temperature that we are going to talk about is going to be called the dry bulb temperature. Now the dry bulb temperature is going to be T sub dB. dB stands for dry bulb temperature. Now what is the dry bulb temperature? Well, the dry bulb temperature is the actual measured temperature. And so you could say that the dry bulb temperature is the same thing that we called the mixture temperature up until this point. This is the temperature if you take your base thermometer and you put it into the room, you read the room temperature of basically the air temperature, and that is the dry bulb temperature. We've just changed the nomenclature a little bit, but it's the same temperature that we've known up until this point. And so if we want to go ahead and take a look at a TS diagram, we said, well, let's draw a state point somewhere out here, right there. Oops, disappeared. We'll go ahead and add that in. But if we wanted to first go ahead and just label this, maybe it'd be a little easier to do this. So we have the dry bulb temperature. We can go ahead and add a horizontal line in. And what we find is the dry bulb temperature. Well, this is where our point is going to be. So this is our actual state point. And we see that we just drew a horizontal line. That is the dry bulb temperature. We could also call this the temperature of the mixture. So same kind of setup that we saw earlier when we dealt with that mixture temperature setup. And so again, all it is a slight change in nomenclature. Now, what we need to do is we're going to add in some lines of constant pressure here. So I'm going to do those in red. So if we had first our line of constant pressure here, and then just to make sure I don't mess this up, I'm going to try and do it this way. So we had our line of constant pressure that goes through that point. And this was the partial pressure of the water vapor. And this was the saturation pressure at the given temperature. And so now instead of being at the mixture temperature, we could say that this is going to be at the dew point temp or the dry bulb temperature. So T dry bulb. Oops. Dry bulb. So all we did is we've now just redefined what temperature. We said, okay, it's now the dry bulb temperature that we find P sub G at, but P sub G stays the same in terms of its definition. And now we still have our partial pressure of the water vapor. And so this looks fairly similar to the diagram that we had a few days, or Monday. Okay, so now if this is the setup, what is going to be different about the next two temperatures? Well, the first temperature we're going to define is, or I should say the second temperature we're going to define is the dew point temperature. And so this would be TDP, so dew point temperature. And so this is the temperature when we would have condensation begin. And so if we think about this, well, dew point temperature, one of the most common things that we could probably associate that was if we think about kind of atmospheric science. And we see when we wake up in the morning in the summer and it's been a little bit of a cool evening, the grass outside will be wet and we call that the morning dew. And so the dew point temperature is basically if we think of it in terms of the atmosphere, it's the temperature that when we cooled the night air down, well, eventually we reached the point where it was at the saturation condition. Saturation condition meaning that we had 100% relative humidity. And then if we cooled it any further, water would start to condense. And so water condensed out onto the basically grass overnight. And then as we raise the temperature in the morning, well, we end up losing all of that water which condensed and it will re-evaporate. And so again, the dew point temperature is kind of, if you think about it in that regards, is the temperature where we get condensation to begin. And so in atmospheric science, that's exactly what we talk about whenever we talk about the dew point temperature, same thing that we're going to be discussing here. Now, in terms of how do we get to that point, how do we get to the saturation point? Well, before we talked about just adding water into the air, and we could reach that by just putting more and more water vapor in. So we added mass of the water and we moved to the left until we reached the saturation condition. And so what we're doing now is we're changing the temperature, but we want the atmosphere to still be about atmospheric pressure. So if we drop the temperature outside in the atmosphere, well, pressure is still going to be about atmospheric. So we said, well, let's assume the pressure stays constant, so the total pressure stays constant. And until we get condensation, we're not going to be adding or removing any water vapor. So that means in terms of our mass fraction and our mole fraction, those will be the same. And that means if our mole fraction is the same, that means our pressure of the vapor is going to be the same. And so just by changing the temperature and the temperature alone, we're going to be moving along the vapor pressure line. And so we said, well, we're going to move the temperature down because we want to cool it until we get to the point where condensation occurs. And so that means we're going to be moving along the line of constant partial pressure until we hit the saturation condition. Now, once we hit the saturation condition, if we cool it down anything beyond that point, we will have condensation. And so we can go ahead and note, if we go ahead and draw a line over like this point, this is the dew point temperature. And so if we wanted to come up with a mathematical description of the dew point temperature, the dew point temperature, T dew point, this would equal, if we look at this, we said, well, this line is now on the saturated vapor condition, which means pressure and temperature are no longer independent because we're on the vapor dome. We're on the very edge of the vapor dome, but we're still on the vapor dome. And that means we can look up the saturation temperature, T saturation, at the partial pressure of the vapor. And so now all we have to know is what the partial pressure of the vapor is. And then once we know that, we just go to the saturation table and we look up what the dew point temperature is. And so the dew point temperature is just, again, the function of the partial pressure of the vapor. And that is all done by table lookups. So you go to the temperature table, you'd find what your partial pressure was, and then you'd have to do a little bit of linear interpolation to find that value. But simply put, the dew point temperature is if we cool it down, if we cool the gas down enough, once we hit a certain temperature, that's where the condensation will begin if we drop the temperature even further. And so other examples of like the dew point temperature would be a mirror that steams up. So like a bathroom mirror, if you have essentially the fog kind of start to cover it, that is an example of the dew point temperature as well. So that is where we will use this. We'll use it as a definition, kind of telling us when we would expect condensation to begin. Okay, so that is the second of our three temperatures, which means we have one more temperature to go. Now this temperature is probably the most confusing of all of the temperatures. It's one that will probably give everyone the most trouble. And it's also one that has a few different ways to define it. Now, generally, we're going to be calling this the wet bulb temperature, though from a pure thermodynamic sense, this is the adiabatic saturation temperature, or T adiabatic saturation. Now, we will eventually make the substitution, and we'll talk about why we can call this the wet bulb temperature, but we'll actually have to do a little bit of mathematics to prove it. Now, what is the adiabatic saturation temperature? Simply put, it's if we have some water and air in a tank and the air is not fully saturated with water, we put it in a box, we get it perfectly insulated, and we let some of the water evaporate into the air until we get we reach the saturation condition. But we only can pull energy out of the air to cause the phase change of the water. And so if the air has to provide energy for water to go through that phase change, so we are basically vaporizing the water, that means we have to put energy in, the temperature of the air is going to drop. And so if we do this in an adiabatic fashion, so all of that energy comes from the air, we would end up moving to a point right here. And so once we reach the 100% saturated condition, that is what we'll call the adiabatic saturation point, or adiabatic saturation. We can also then substitute this as basically what we call the wet bulb temperature. Now we'll get into why we call it the wet bulb temperature here in a little bit. Now this does have some important parameters, but before we can talk about why this is important and what processes these would be important for, we kind of have to figure out what it is, how is it going to be defined, and how historically has this temperature been used. And so that's what the next few slides are about. And so what we want to do is we want to figure out how to model the wet bulb temperature and maybe do a little bit of our first approach at putting some psychometric terms into use. Now, the key concept that we're going to do is we're going to have air that's got a little bit of water vapor in it, but it's not going to be saturated. So we have a really, let's say, a relative humidity that's going to be below 100%. And so that's going to come into this tank. Now this tank's going to have some liquid water at the bottom, and we're going to blow the air that hasn't been fully saturated over it. And it's going to be a really long tank, and we're going to assume that it's long enough that we get enough water to evaporate into the air that we leave at the saturated condition. Now, saturated condition means we have a 100% relative humidity. We can't take any more water on in this air, so it's fully saturated. And we're going to have that leave at state 2. And what we'll model this as is we'll model it as we just put a little bit of water in, so we maintain a constant water level. So we'll have some water being added into this system. So to do this, we're going to have to go ahead and apply our conservation of mass and conservation of energy, and we'll see how we can define this concept. Now, the concept that we want is we want to figure out what is T2, because T2 is the process where we've had this insulated tank. So we should also note there's no heat transfer out of this tank, so it's adiabatic, and we are going to get it to the saturated condition. So T2 represents the adiabatic saturation temperature. Now, to do this, we have to spend a little bit of time going through all of our key terms. And so the first thing that we're going to want to start with is we are going to do conservation of mass. And so we'll recall in thermodynamics, conservation of mass, we have dm dt, so the mass inside the system, change in mass inside the system with respect to time. This is equal to the sum of all of the mass flow rates in minus the sum of all the mass flow rates out. And we can go ahead and assume this is done at a steady state. Now, doing it for the total system is possible, but it's not going to be the best use of our energy. We want to focus and do a per species mass accounting. So to do this, we're going to break this apart into our 2 species. The first one we need to do is air. So if we just do a mass balance on our air, we could just go ahead and say we'll do it here for this first one. So we have the change in mass of air with respect to time inside the system. This is equal to the mass flow rate of air in minus the mass flow rates of air out. And we assume that it's steady state. What we'll end up with is, well, steady state, left-hand side goes to 0. Mass flow rate of air in, that would be the mass flow of air at state 1. So mass flow of air, state 1. And we have 1 exit for air. So we have minus mass flow rate of air at state 2. And so the result of this ends up being that we can just go ahead and say, well, we have a mass flow rate of dry air. This is just equal to state 1 and state 2. And so that one gave us something useful, but it's not what we really wanted to find out. So we will use this, but we could probably infer mass flow of air in has to equal out for this case. Where things get a little bit more interesting now is if we repeat this for water. So we've done our second species accounting. And so we can go ahead and do the same thing, dm of water, dt. This, again, steady state, this is going to go to 0. Well, we're going to have the sum of all the mass flow rates of water in minus the sum of all the mass flow rates of water out. And we said, okay, sum of mass flow rate of water in. So let's go ahead and just put this side was 0, mass flow rate of water in. And so if we look at this, we looked at state 1, we said, well, this has some relative humidity, which means that it has some amount of water coming in. So we'll have a m dot vapor 1 coming in here. So we'll have a mass flow rate of water vapor entering the system at 1. We said, well, this is going to be saturated. So yep, we're going to have water vapor now leaving at state 2. So minus m dot vapor of state 2. But what we have to pay attention to is we have this liquid water coming in at the bottom to make up for the liquid that evaporates into the air. And so we have to go ahead and add in the flow of our liquid water, which I'm just going to go ahead and call W for liquid water. And so noting that we can go ahead and rearrange this, we could say solve now for the mass flow rate of the water. This is going to equal the mass flow rate of the vapor at state 2 minus the mass flow rate of the vapor at state 1. Then I said, okay, that makes sense, but how is that going to be useful for us in our analysis? We really want something that's going to help us move forward. Now the trick to this comes from our base definitions. So if we recall, the humidity ratio, which is equal to the mass of the water vapor divided by the mass of the dry air. We said, well, mass flow rate, we could probably add a dot on top of that. We could add a dot on top of that. That looks pretty good. So we can say now we have the mass flow rate of the water vapor. So it would equal the humidity ratio times the mass flow rate of the dry air. We'll renote that. Okay, there we go. Dry air. We said, okay, if we go ahead and now make this substitution in, well, mass flow rate of air for state 1 or state 2, doesn't matter, same thing. So making that substitution in over here, well, mass flow rate of the water, well, it'd have mass flow rate of the dry air times the humidity ratio at state 2. This would be W2. And then we could do mass flow rate of dry air times W1. And so we've now changed our mass flow rate equation into something that's related to the mass flow rate of our dry air and our two humidity ratios. And so we'll be able to make use of this when we get to the next part of the setup. The next part of the setup is going to be applying conservation of energy. So writing out conservation of energy, we can say that in the system we have dE dt is equal to the sum of the heat transfer rates in minus the sum of the rates of work out. Then we have plus the sum of the mass flow rates in, enthalpy plus kinetic energy plus potential energy all in, minus the sum of the mass flow rates out times the enthalpy plus the kinetic energy plus the potential energy out. And we said, okay, if we go ahead and apply some assumptions, we're still going to assume steady state. We're going to assume that it's adiabatic. In this case, we're assuming there's no work. So now we just have to sum up all of the mass flows. And for the mass flows, we can assume that there's going to be no kinetic or potential energy changes. And so what we get is on the left-hand side, we have this is equal to 0. Now we have to sum over all the mass flow rates in. And so we'll have the mass flow rate of the dry air in. So I have m dot air. And I'm going to go ahead and bulk these together. So we'll have the enthalpy of the air at state 1 minus the enthalpy of the air at state 2. So then take into account air exiting, or leaving and exiting the system. We can then say, okay, if we have air, let's do the water vapor in. So we have plus m dot times the water vapor in. Water vapor in, that's state 1. We have the enthalpy of the vapor in at state 1. We now have the enthalpy of the water vapor leaving at state 2. So m dot vapor 2, enthalpy of the vapor at 2. Plus then we have the enthalpy of the water coming in. So we have to add in m dot water times the enthalpy of the liquid water. And so we'll call that just the water coming in. Now what we're going to note is that if we go ahead and do a little bit of a substitution here, what we'll end up with, and we can say, well, we know that we can use the vapor is equal to the mass flow rate times the of dry air times the humidity ratio. So we're going to do that right here and right here. And then we're going to do this over here. And we see that we'll end up with a mass flow rate of dry air in each of our terms. And so we can go ahead and say, well, we could bring that out, and eventually we'll cancel this out. And in terms of the dry air, we'll have h of air 1 minus the h of air at state 2. Actually, no parenthesis just yet. Well, we'd have now mass flow rate of the dry air times the humidity ratio at state 1, so W1 times h of the vapor at state 1. Mass of dry air came out. Repeat the process for state 2. We have a minus humidity ratio of 2, h vapor at state 2. And then we can do mass flow rate of water, mass flow rate of air comes out. We have now plus humidity ratio of 2 minus humidity ratio of 1. And what we're going to say, this H sub W, the water coming in, that would be the liquid state. So we'll assume that is on the liquid side of the table. So we're going to assume H sub F. So that would be over here. This would actually be technically state 2, be this point right here. So we'd look up H sub F. So that would be the liquid side of the table for our lookup. Okay, so we've made those substitutions. So we go ahead and add this in, and we end our parenthesis. And so what we can do is we can go ahead and do one more form of rearranging, and that is going to be, we can go 0. We note that the change in the enthalpy of the dry air, that can be related to C sub P of the air times T1 minus T2. We then can go ahead and add in the humidity ratio times the vapor state at 1. We'll go ahead and say instead of vapor, we'll go ahead and add that's G here. And we have minus the second part, which would be W1. Yeah, this would be the enthalpy of G at 2. And then we have minus W2. This is going to be H sub G at 2 minus the H sub F. And I'll note that H sub F is going to be at state 2. And actually, I think this is supposed to be F2. There we go. Sorry, that was my mistake. That is F2, not HG2. Okay, and then that is going to be it for this form. Now what we're going to note is H sub G2 minus H sub F2. That is H sub FG. And so FG was the change from the vapor state to the liquid state. And so we now have the phase change term in this setup. Now, why is this going to be important? Well, we're going to go ahead and move to the next slide, which is going to just reset things here. And so what we're going to do is we're going to rearrange some terms. And so this is, again, just finishing up where we left off. And what we'll find is if we solve for the humidity ratio at 1, we'll have C sub P of the air. We then have the temperature at state 2 minus the temperature of state 1. We then have plus the humidity ratio at state 2 times H sub Fg, so that's our phase change at the given temperature, divided by H sub G at state 1 minus H sub F at state 2. And so state 2 just means it's a function of temperature at 2. Now what we're going to recall is temperature of state 2, that's going to be 100%. So remember, state 2 is saturated. So if state 2 is saturated, that means the relative humidity is equal to 100%. And so if it's equal to 100%, what that means is the humidity ratio, so equals 0.622 times now P sub G at the temperature 2 divided by P minus P sub G at temperature 2. Now, why is that important? Well, if we make this substitution in here, we're going to see the humidity ratio at state 2, which is, again, going to relate to the saturation condition. That's only going to be a function now of temperature 2, because the pressure of the saturation condition is going to be a function of that temperature. We look at H sub Fg. This is, again, at state 2, so this is a function of T2. This is a function of T2. This is a function of T1. And C sub P delta T, that's a function of T1 and T2. And so what we really just wrote out is the humidity ratio at state 1. This is a function of T1 and T2. Now this might seem a little bit weird. Why did we talk about this adiabatic saturation temperature, which is T2? So again, adiabatic saturation temperature. This is T2. Why are we trying to now solve for the humidity ratio, assuming we know T2? How does that help us? this doesn't seem quite the way that we thought this would go. What we thought we could do is we'd solve for T2, which would be the adiabatic saturation. We said, well, we thought that'd be a function of humidity ratio 1 and temperature 1. That's what we thought we would do. But if we take a look at this equation, yeah, could we do it? Well, it's possible, but we probably want a computer to do it for us because of the sheer amount of table lookups, because a lot of these details are now hidden in that thermodynamic property data. Now, why did we instead write it this way? Well, the truth of it is the temperature of state 2, we've noted this is what we're going to call the wet bulb temperature. This is going to be the temperature that happens when we adiabatically saturate the air. T1, well, that was the dry bulb temperature coming in at state 1. And so what we end up noting is that what we're really going to say is that if we want to figure out the humidity ratio at 1, we could now say this is going to be a function of the dry bulb temperature, TdB, and the temperature of the adiabatic saturation. And so we see that we now have two temperatures that our humidity ratio is a function of. Now, why is this still important that we kind of reframe it in this way? Well, if we can, say, measure the adiabatic saturation temperature, we could now use that to calculate our humidity, or I should say our humidity ratio. And so this is what was done historically. We figured out how to measure the adiabatic saturation temperature. We would know how to measure the dry bulb temperature. We could then immediately go and calculate the humidity ratio. So this is where the adiabatic saturation temperature becomes very important. It was used as the method to calculate our actual humidity. And so how do we now measure this adiabatic saturation temperature? We could develop a tank like this that we just did for our theoretical setup, but that's not going to be convenient in every case. What we want to do is we want to develop an instrument where we can do this in the field. Now, the easiest way to do this is we took a ordinary thermometer. We added a wick, so just some sort of cotton, something that's got a high porosity. And we dipped that wick into the water, and we made sure that the wick was attached to the end of the thermometer, and we blew a bunch of air across it. Now, this form of the thermometer we refer to as a wet bulb thermometer, because why is it called a wet bulb? Well, we took the bulb at the end of the thermometer, we added a wet wick to it, and we blew air across it. And so that's where we get the name wet bulb, because we got the wick wet for this measurement. Now what this does is the air comes across the wick, and we basically have this mini container inside of the kind of wick. So this is a very porous material. So the air causes the water that's on the thermometer to evaporate. And when that evaporates, well, the temperature will cool down a little bit, and we're able to read approximately the adiabatic saturation temperature. And so if we can read the adiabatic saturation temperature, so it'll just be this measurement right here, we just need the dry bulb temperature, which is just a regular thermometer, and we can now make the calculations necessary to determine the humidity ratio. And so what we did is we said, well, let's develop a device that can do both of this. And we came up with the sling psychrometer. Now, the sling psychrometer is basically two thermometers. One is the dry bulb, so no water on the end. One is the wet bulb thermometer, which has a wet bulb wick. There's water, and we need to get air to flow across it. And this is where the sling part of it comes in. So we grab this handle, and we spin this around and around, and we get the airflow necessary to essentially approximate this condition that we had up here. And we are able to then read two temperatures, a dry bulb and a wet bulb temperature, and we can now make that calculation. So this is historically why the wet bulb temperature is very important. It's going to help us calculate things. Now, we're going to get into next week, we'll talk about a chart that's going to be very helpful and useful for that purpose. And this is, again, why this setup is important. Before we do that, I want to just go ahead and talk about what do these temperatures relate to. And so, again, dew point temperature is going to relate to condensation. And so condensation is important in terms of equipment design. So if you don't want water to essentially develop on your equipment, so if you have a cold like cryogenic pump or something like that, you don't want water to get on that. It could damage it. So that's where you're going to pay attention to the dew point temperature. It's also important if you're manufacturing any sort of electronics, you have to keep your air temperature for those electronic manufacture above the dew point. Otherwise, you might have water droplets that condensate onto your small electronics manufacture that will basically destroy the electronics that you were making. And it's also important if you have to worry about something warming up. So example of something warming up is if you take a soda can out of the refrigerator, well, the water that you see on there, that forms because the air right in contact with your can is going to drop below the dew point temperature. Water will come out of the air and condense onto your can, and that will also warm up your can during that process. So that is some kind of comment on the dew point temperature. Now, the last thing I wanted to comment on was the wet bulb temperature, because this again is the new one that seems a little bit weird. Now, in terms of its use, it's going to be very useful if we have to do cooling tower analysis. So if you do a wet cooling tower analysis, similar to what we saw in the lab in week 2 when we did the chiller, well, we would be focused on the wet bulb temperature because you have air coming in, you have some water, it probably is going to leave at a saturated case. And so you can only put as much water and you can only get so much heat rejected by that for that phase change by that air coming across. And so you're limited by the wet bulb temperature for that type of heat exchanger design. It's also very important in terms of humans. So when we sweat, it's going to be important to know what the wet bulb temperature is, because if we have a very high humidity case and it's very warm outside, well, our sweating is not as effective at cooling us off as if it was a low humidity case. And so that is another case where wet bulb temperature is going to matter. And then the last thing that we'll note is kind of the history, and this is going to be done using the psychometric chart. And we'll talk about this in, I think, probably about a lecture and a half when we actually get into the psychometric chart, and we'll see how the wet bulb temperature plays a role in that. Okay, so that is where we're going to end today. I think I'm went slightly over today, but we'll pick up with the example problem on Monday. So if you have any questions over the weekend, or if you have any questions on the lab report, please let me know. Otherwise, just the last reminder here, there is no class tomorrow. It is your spring break, so enjoy your long weekend, and I will see you again in class on Monday. So have a good mini break and weekend.
Thank you. You too.
Thank you. Have a good one.
Thanks. You guys too.